Hello. Hi guys, good morning. Welcome back to a new video. In this famous problem, count pairs of connectable server in a weighted tree network. It's a question number 3 of today's bi-weekly contest. Question number 4 is already live. Let's see. The problem says it says that you're given an unrooted weighted tree with n vertices. Now there is no root. Again, you have usually seen the problem where a root is given to you, then you go to left, right. But now when you are given an unrooted tree, it's actually referring to a graph structure that has only n minus 1 edges. So that's a tree. Okay, representing a server, and that tree structure represents the servers, and the nodes are actually the server nodes. And we said that we have n vertices, which means n nodes, and every node is numbered from 0 to n minus 1. Great. Now we have an array edges where edges of I is nothing but, it's a weighted tree, which means an edge I represent by saying ai to bi, I have an edge with a weight of w of I. Okay. Now I am also given one integer which is called as signal speed. Okay, what that signal speed is and what's the use of it, we will see later on. But yeah, this is what we are given right now. Now, two servers A and B are connectable through a server C if, again, A and B are two servers, because we remember nodes are servers for us. They are connectable through a server C if, what's the condition if? Firstly, A is less than B. Okay, A is less than B, which means A I can make a small, okay, B is more. Okay, that's one thing. Aryan, what is the significance of A is less than B? We'll see that. But yeah, this is what we are just plotting what the question is asking us. And A is not equal to C. Yeah, which means both A, B, and C are different nodes. A, B, and C are three different nodes for us. The distance from A to C, okay, is divisible by signal speed, is divisible by whatsoever the distance is. Again, I can find the distance by using multiple nodes in between. So the distance, actual distance, if that is divisible by signal speed, okay, and the distance from C to B, again, that can be via multiple nodes also, that distance, if it is also divisible by signal speed, and the path from C to B and the path from C to A do not share any edge. Path from C to A and path from C to B, for sure, both are different, both are not sharing any edge. Then I can simply say that C is a connectable, A and B are connectable via a server C. Aryan, I understood the point 2 and point 3. First point I didn't understand is point 1. And next is I didn't understand point 4. What actually is the significance of these points? So bro, let's come on to point 1. What is the significance of the point 1? But before that, we'll come on to point 4, because it will complete the picture for us. Point 4 simply says that the path should not share any edges. Aryan, I can simply see in front of my eyes that path from C to A and path from C to B will never share the edges. Why are they saying they will share the edges? Because what if I ask you, node A would have been like this, node B would have been like this, right? And node C would have been like this. What if the node connecting to them would have been something like this sort? So you saw that this A to C connection and this A to C connection shared a path. Oh, which means I cannot have some connection like this. I want, okay, if I have one node A on this side, so other should be on the other side. Others should be on the other side. That's it. It should not go in from the same side. That should not be there. Okay, great. That is one thing which point 4 is saying. Point 2 and point 3 are simply seeing the distance. Now, as soon as you hear the distance term, for sure one thing have clicked your mind is Dijkstra's. Again, I'm not saying it is applicable, but it should be clicked. But we also see that we have to find it, which means we have an array called as count of length n, where count of I is the number of server pairs. You remembered what is a countable pair? That are countable through the server I. So in this place I have a I, and then number of such countable server pairs from that server I, that is nothing but my count of I. So ultimately I am saying, okay, Aryan, is it saying that I have to find distance from one node to every other node? Is this what it is saying? Maybe, bro, maybe not. Let's see. But yeah, we got to know one thing, that something they're talking about distance. They are talking about that distance should be divisible by SS, which is the signal strength. And to find the distance from one node to any other node in graph, we have Dijkstra's, but we know it's a tree. It's a tree, so we can also use a simple DFS or BFS traversal. That's completely fine for a tree. For a graph, we need that kind of structure, which means Dijkstra's and all the other algorithms. Comment down below. I am saying Dijkstra, that's a single source shortest path. If in this problem you can easily see, I have to find the shortest path from one node to every other node, and from all node to all the other node, then which algorithm you must have thought of? Comment down below. Again, I'm not saying it is applicable, but just comment down below for the general knowledge of your and the audience. Now, coming on back, we saw that it's a simple tree. Now, to find the distance from one node to any other node in a tree, I can simply apply a DFS traversal. Simply, a DFS traversal will work because it's a tree with us. And point 3, sorry, my point 4 makes sense. Point 1 is still remaining, Aryan. What this A is less than B saying? Is this actually something, or they are just fooling us? Bro, it says something. What it means by this is that if A is less than B, so I will count this as one pair, which means AB is one pair which is connectable through C. I will not count it again, which means BA is not a pair which is connectable through C. So it simply means that one pair will be counted just once, not twice. So this is referring that I should not count a pair twice. Now we have understood the problem. Let's see that how we will solve it. Now, one very basic thing which comes to my mind is, bro, Aryan, my basic need is that I want to find the distance from a node. Like, again, I have to find the answer for all the nodes. Here I is from 0 to less than n. So I have to go and find all the nodes. I will keep my node I. This is the server C is node I for every node. I have to go to every node, and from that specific node, I will have to go and find the distance to all the other nodes. Which means one thing, I don't know the answer. I don't know how that can be implemented, but one basic requirement is that I will go into every node. For that specific node C, I will go and find the distance to all the other nodes. Again, that can be a tree, bigger tree also, but all the other nodes. And again, we saw that to find the distance from a single node, again, let's imagine this. Again, what I'm saying is I'll consider one node as a root node, and I can simply find the distance to all the other nodes. So that distance finding, a simple DFS, can be done in O of n time for one root. But I told you that my root will keep on changing at every I. Oh, so I'm saying, okay, I'll keep on changing. I keep on changing my root. I have n roots. I'll keep on changing my root, and every root, I have to go and find the distance. Again, how to handle that distance and stuff, we have to see. But roughly, I can easily imagine that my time complexity will actually go to O of n square. Will this work, or shall I think of something else? Oh, n is 1000, which means n square will work. I can go on every node as a root node, and then if I can find the distance very easily. So n square will work. Okay, so right now what I'm going on in the path, considering it's a contest, I should go on at that path only. But Aryan, you forget, you have to find, okay, you consider this node I as a root node, but then your main task was to find all the pairs A and B which are connectable through a I, which is the root node which we have considered right now. So I'm just considering right now, okay, I will go on iterate every node, and I'll think that as a root node, which is a connecting node, which means the node C. And then I have to find out how many such pairs are there, AB. Now it's a simple math problem. That how you thought of it, simple math problem? Because we have seen this problem quite a lot previously, and that's what practice comes in. That, okay, we thought, okay, that's a root node, simple root node. Now I can have a simple connection of nodes. One thing we thought of. If A is lying here, B should lie here. or B should lie here, or B should lie here. It can never lie here. Why? Because you remembered, if this is the root node, so my B node should lie on the other end of my node, of my root node. As you forgot, like I don't think that you have forgotten, but if you have to remember, right? It should not lie on the same side, which means it should not lie on the connection. This is the connection. A is connecting via this, so it should not lie in this connection. It can lie anywhere. Node B can lie anywhere else. So I got to know one thing. That if this is a node, number, again, considering, again, connection will only build when the distance to this node D and distance to the other node D. If this D mod SS is signal speed. If this is mod A, then A and this specific D, which means, okay, let's say this node is B. So this B mod SS, sorry, this D mod SS is 0, which means this specific D. Then this A and B can form a pair. Aryan, then this finding pair and stuff will again take offense to a time. I don't have that much time. I know I can simply go and apply my simple DFS to find the distance, which means this finding distance for me is easy. So I can find the distance at up till this point. Let's name it as, let's number the nodes 1, 2, 3, 4, 5 and 6. So I can easily apply a DFS traversal. I can go and find, okay, D1, then I can simply propagate the distance, find D2, find D3. See, it's a simple DFS traversal. If you don't know how to find the distance, I'll quickly tell you that if you have to find the distance, let's say here the node is root node. Here the node is 1, 2, 3, 4, and let's say 5. So you know the weight of these edges. Let's say W1, W2, W3, W4, and W5. Weight is given. You will simply do a DFS traversal. Then initially the distance is 0. Here you will propagate, the distance will become W1. Again, let's take the different color. Here the distance is 0. Distance will become W1. Propagate the distance downward. Here the distance will become W1 plus W2. Here it will become W1 plus W3. Here it will become W1 plus W4. Here I'll propagate it much further. Here it will become W1 plus W3 plus W5. And that's how I can simply find distance to every node. That's completely fine and okay for me. Okay, great. Now comes the fact that I am easily able to find the distance to every node. But good nodes are the one which have distance mod SS equal to 0, which is divisible by signal speed. So I have found the distances. Okay, that's a D2, that's a D5, let's say, that's a D3, that's a D4, and that's a D1. Let's say I found the distances. But out of all these distances, whosoever is divisible by signal speed, that's a good distance. That's a good distance. Maybe it is not a good distance. Maybe it is not a good distance. It is a good distance. So these are the good distances for us. So now I got to know easily one thing that, okay, in O of n time, I can figure out what all are the good nodes. What are the good valid nodes? Okay. Now I can think of, okay, this 2 is a good valid node. This 1 is a, let's say, good valid node. Again, how I say good valid node? When their distance, again, my first task was to find the distance and then check if the distance is mod SS equal to 0, which means when the distance is divisible by signal speed, then that's a good node. Okay, let's say this is a good node. This is a good node. Now, when I have found a good node, now my task is to find the number of pairs which are connectable through root. Now, okay, for sure the number of pairs valid candidate can be this node, this node, this node, and this node, which means valid candidate are node 2, node 1, node 6, and node 5 only. Now, as we saw previously earlier also, that my one portion, what all nodes are there, can form the pair with other portion. So this 2, he cannot form a pair with 1, but he can form a pair with node 6 and node 5. 6 and node 5. Let's change the color. So he can form pair with the node 6 and node 5. So I can say, okay, 1 from 2, I can make a pair with node 6 and node 5. Okay, great. Which is, okay, this 2 to 6 is one pair, 2 to 5 is one other pair. Again, I will not recount that pair, which means I can say, okay, node 6 to node 2 is one pair, node 6 to node 5 is also one pair. Or I can say that, okay, I'll tell you what I mean by that. Okay, node 2 I got it that okay, node 2 to node 5, sorry, node 2 to node 6 is a good pair, node 2 to node 5 is a good pair. Then let's try with the node 1. Okay, node 1, I know, okay, node 1 to node 6 is a good pair, node 1 to node 5 is a good pair. Again, okay, let's come to node 6. Node 6 to node 1 is a good pair, node 6 to node 2 is a good pair, node 6 to node 2 is a good pair, node 6 to node 5 is a good pair. Okay, great. Node 5, okay, let's put it here itself. Node, let's erase this and put it. Node 5 to node 6 is a good pair, node 5 to node 1 is a good pair, node 5 to node 2 is a good pair. Now you saw one thing, that I repeated some nodes, and that's exactly duplicate. So node 5 node 2, node 5 node 2, repeat it here and repeat it here. I can only take one. That is what the problem was demanding. I can only take one. So I can simply say that whatsoever pairs I have got, I can simply divide that by 2, which means remove or snap half of them. So I'll snap this because I've taken this. I'll snap this. I've taken this. I'll snap this. I have taken this. I'll snap this. I have taken this. I'll snap this. I have taken this. So now you will see 1 2 3 4 5 6 7 8 9 10. Now I had 10. I snapped half of them because I know my condition number 1. I'll remain with simply 5, and that's my answer. Oh, Aryan, that's good, that's great, but can you just repeat on how did you find these pairs as an answer? Simple maths. How? If you remember one simple maths, okay, you had two options here, you had one option here, you had one option here. Now I ask you, how many pairs can you make from this two? With these two balls and this one ball, I can make 2 pairs, this and this. Okay, great. These 2 balls and this one ball, I can make 2 pairs. Okay, so with these 2 balls into my 1, I can make 1 pair. With these 2 balls, with this ball, I can make again 1 pair. Again, with this one ball, I can make 2 pairs with this. So 1 into 2 for this. With this one ball, I can make again 1 pair with this. So 1 into 1 with this. Aryan, it's confusing. Take a bigger example. Okay, no worries. I'll take a bigger example. So as I told you, let's only take the valid nodes. Let's make the valid node structure. Now here I have, let's say, plotted only the valid nodes. So this is valid, 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 this is valid. Let's imagine all these are valid nodes. Again, you know how to find the valid nodes. Let's number these nodes: 1 2 3 4 5 and 6. Now I am asking you, find the number of pairs. You know these 3 are valid. So the count is 3. Remember this count. This is valid, count is 1. This is valid, count is 2. So Aryan, you are saying that firstly you will go and do a DFS, find the distance, then you will check that if the distance mod SS is actually equal to 0, then you can imagine that for that specific subtree, this is a good node. If this is a good node, simply increase the count. Okay, so far so good. So you know the steps, but now you have to find the pairs. So you simply saw that with this 3, all these 3 nodes, I can form pair with this one node. So 3 into 1 will be the number of pairs. You can simply see 1 1 4 3 4 2 4. Okay, then from 3 I have 3 here, 2 here. So for sure, simple maths, 3 here, 2 here, you can form 6 pairs. 3 into 2, how? You can see 1 5 3 5 2 5 1 6 3 6 2 6. Okay, form 6 pairs. Great. Now this as the first node done. Let's come to here. From this 1 to this 3. Again, Aryan, you have counted 3 to 1. So while counting again, okay bro, I'll simply count, but I'll in last divide by 2. So as to make sure I'm not doing anything weird, anything out of ordinary, adding some if condition stuff, I'll not do that. I'll simply do a by 2 in the last. Okay, from 1 to 3, I know 1 node here, 3 nodes here, I can form 3 pairs, which means 4 3 4 1 and 4 2. So I can form 1 into 3 pairs. Okay, from this 1 node to this 2 nodes, again 1 node 2 node, so I can form 1 into 2 pairs, which means 4 5 4 6. Great, this node is done. Now comes the last node, which is 5. Again, that's the last count which I have got. Count, okay, 5. Again, for this node 2, for this with this node, 3 nodes. 5 2, 5 1, 5 3, 6 2, 6 1, 6 3. I know 2 into 3 is the count. And the same for this, 2 into 1 is the count. This is the total count which I have got. Simply whatsoever the sum you have got, that's the total number of pairs which you can actually achieve. Divide that by 2, and that's your simple answer. But bro, Aryan, you are actually going, which means for this node you go on to all the other nodes. For this node again you go on to all the other nodes. For this node again you are going to go to all the other nodes. So that's a O of n square thing which you are doing. You cannot go O of n square, because O of n itself you are doing when you are trying for all the root nodes. For one root node, okay, where is it gone? Yeah, for one root node you can at max to O of n. You cannot apply this. Bro, you are absolutely correct. If I ask you what is this value, then you can simply say, bro, I can see one thing, that if I have a 3 here, then I can take this as a common. Okay, 3 I take as a common, it become a 1 plus 2. I can take a 1 common. Okay, 1 common, 3 plus 2. I can take a 2 common, it will become a 3 plus 1. Bro, still it is not becoming a formula. Bro, because this 3 I'm multiplying with all the other values except me. So I can simply say, if I can imagine this as sum minus except me, which is 3. I can say this as the sum minus except me, which is 1. I can say this as a sum minus me, which is 2. And thus I can simply go and find, firstly my main aim will be go and find the distances. Then from that distances I will go and find what are all the good nodes in that specific subtree. Okay, when I've found the good nodes in that subtree, I'll grab the sum of that count. Okay, I have got the sum, and then I know the count, the good node count in all the subtree. I can simply go on that good node count and say, okay bro, right now is 3. So the contribution of this node 3 will be nothing but 3 multiplied by sum minus 3 itself. The contribution of this will be 1 multiplied by sum minus 1. The contribution of this 2 will be 2 multiplied by sum minus 2. And again, in that you have counted twice. So please do a division by 2 in the end. And that's going to be your answer for a node which is a root node which you have chosen. And repeat this process for all the nodes. And that's how you can simply solve this answer. Now, let's come on to the code. It's exactly same as what we discussed. Firstly, we have given some edges as the input. So for sure, we will have to build the graph by ourselves. So what we will do is we'll simply firstly grab the n. We know it's a tree. So it will have n minus 1 edges. N minus 1 edges, right? So this edges size will be n minus 1. So if I add a plus 1 in this, I will get a n. So I just did edges size plus 1 will be the n for me. Okay, great. Now I just took a global variable which is signal speed, although you can also pass it as an argument, but to make it a clean simple code, I took a global variable. As you can see, I took a global variable. My one variable global is n. That's not required to be global, but still to make it consistent, I took a global variable. Other variable is count. I'll tell you what the count is. That count is the number of good nodes in that specific subtree, and the s is the signal speed. And this is my global variable, which is graph. As you know, it's a adjacency list to node to a pair. So it is, if I just tell you, if you don't know what the adjacency list is, then okay, 1 2 the weight is 4, 1 5 the weight is 6. So I am saying 1 to a pair which is 2 comma 4. 2 is the node v, and this is the distance, comma I can say 5 comma 6, node v and distance. And that's how I can simply plot my adjacency list. That's a simply. You can also take it as a you can also take it as a vector itself, which means this can be a vector also. But yeah, it depends upon you how you want to build your graph. Now we will simply go on and iterate on all the edges and build our graph itself, which means from u to a v comma distance, v u comma distance, because it's an undirected graph. Now when this entire portion is done for us, I'll simply go on and now try to find the answer. This f answer is the final answer which I want to deliver. But as you remembered, I will go on to all the nodes as a root node. So I'm going on to all the nodes. Here I'm going on to all the nodes and thinking them as a root node. This is the parent, which means, okay, that's a root node for me. Now, for this root node, I have to go and find the answer. What is the answer for this? And I will simply say, okay, f answer of my parent is answer. Now, remember, this is the root node, is the answer. So I will compute the answer for the specific root node right now, because I know I can do a n square very easily. Okay, great. This is the sum. What is the sum? If you remembered, I have to keep track of the sum. I have to keep track of the sum. So I will keep track of this specific sum, which will help me to optimize my answer. Now, I will go on to all the childrens of my graph node, and then we'll do a DFS traversal on the children's itself. And firstly, it is only children, not children's. Secondly, why are you only going on to the children? Because bro, if you remembered, I want to build the graph. I cannot just indirectly and blindly go on and say, bro, go on to the child and find. I want, okay, go on to one node to my child, and then traverse this entire subtree. Go on to other node to my child, then traverse the entire subtree. Go on to other node to my child, and then traverse the entire subtree. So my first operation is go on to my child and then traverse the entire subtree. So it's the reason I will firstly go on to my child, and then apply a DFS function, and then traverse my child. Now this is simply traversing, which means this is the child, this is the parent, and this is the D. Now in the graph, when you are given that's graph is a tree, you don't have to plot and simply say that, bro, it is visited, it is not visited, all that stuff. You can simply keep track of the parent itself, because you will not have a icon, so you don't need to keep track of the visited array. You can simply keep track and say, I will not go to my parent, and I can simply go to my child. So I'll simply say that's how you can traverse your simple graphs. Now, which are trees. Now you will simply go on to child, take the parent, and the D is the distance. Why is that needed? Because maksad nahi bhulna. Your aim was to find the good nodes. Good nodes are the one whose distance mod SS is 0. So I will keep track. That's the reason I took the global variable as count. This count will keep track of the good nodes whose distance mod SS is 0, and that's a good node for me, and I'll keep track of the count of that good nodes. I'll come on to my DFS, simple DFS. I'll keep track. Okay, if distance mod SS is 0, simply increase the count, then go on to the children of that node, and then if the child is not parent, simply go and do a DFS and simply increase the distance, as I showed you in the dry run also. Now when this entire portion is done, you have actually traversed the children, that specific child of the node. Now one specific child is traversed, which means I have got the sum. I'll keep track of the sum, because I know this count will give me number of good nodes for that specific child, and I'll go on to all the childs. I'll keep on pushing the corresponding values in the temp variable, in the temp vector. So if you know what this value in the temp vector will pushed on, so temp I will pushing on node like value 3, value 2, and value 1, which is the count of good nodes in that specific subtree. And also I'm parallel keep on tracking my sum, which is 3 plus 2 plus 1. Why is that needed? It is needed for this specific thing. And why is this needed? This is needed because I will traverse it again and will find the value. Again, you can club this in one loop also, but for simplicity and for explanation, I took it in 2 loops. So I will do simply iterate again back on temp vector, and then answer contribution for this specific will be 3 multiplied by sum minus 3. Cool. So I'll come back, and when this is done, I will again iterate back on my vector temp, and then answer contribution will be sum minus element into element, and that is the answer contribution for that specific node. Simply push back as I showed you. Final answer for that specific root node will be answer by 2, because you are counting twice. You want to only count once, and return the F answer. By this, you can simply see that you have solved this in O of n square time. And for sure, you know that you are building this specific graph. The graph will have at max n edges. So I can roughly say it will have 2 into n nodes in my entire tree. So this will take n space. This entire thing you guys simply build in a graph doing a DFS worst case takes n space. So your space will be O of n. Again, n plus n plus n for multiple stuff, but yeah, roughly it is O of n. And that is your final complexity, which will actually work for you. Cool. I hope that you guys got understood everything, how in the DFS, how maths, all that stuff is working. Cool. Bye bye. Thanks so much. Goodbye. Take care. Bye.